So we'll go ahead and get started um, with this week's homework. We might go a little bit longer today. These problems are a little bit more involved just because of the main topic that we're incorporating this week, which is that of the force of friction, which is a little complicated to deal with. So I'm going to start with just a quick conceptual review about the force of friction, what makes it so complicated. So there are two types of friction that we're responsible for in this class. One is called static, and the other is called kinetic. Kinetic friction will be when your object is in motion. This one's going to be the easier one to deal with. Generally people have an easier time with this. You'll have, a block on a surface, and the surface will have some friction, and you'll have what's called the coefficient of friction, coefficient of kinetic friction explicitly. And if your block is moving with any velocity whatsoever, you're going to be undergoing kinetic friction. You'll have a kinetic friction on the block. And that kinetic friction force is always going to oppose the direction of the motion. In other words, this is the force that would slow an object down naturally. There's your F sub k. And to calculate it, the calculation is relatively straightforward. It's just the coefficient of kinetic friction times the normal force. Now, this is the calculation for the magnitude of the coefficient of kinetic friction. However, the direction obviously will come from the diagram itself. What you'll notice, especially if you have done enough practice with the normal force, that you know that the normal force is perpendicular to the direction of motion. So, for instance, in this diagram, your normal force would be up. You'll notice that that's perpendicular to the force of kinetic friction. And so you can hopefully sort of get the idea here that we're going to have to be doing both the x and y independently, but then tying them together with a calculation for friction. Static friction, on the other hand, static generally means at rest. Those of you in the engineering field will take a class called statics in a few semesters, which is just a static force problem. Because of the way that the force of friction opposes the direction of our motion, when our object is staying at rest, what's going on there is that the force of friction is opposing the direction that the object wants to move. So what this means is if I were to plot the force of friction versus, well, we'll just go ahead and call that the static friction. The force of the static friction versus the applied force. Okay, I don't know why it's not letting me. Okay, anyway, if we were to plot these, so if I'm not applying any force to an object, like if you were to just look at the desk that you're staring at, there's no frictional force that's pushing back against your applied force. The frictional force has to be reactive. So when there's no applied force, your force of static friction will be 0. And as I increase my applied force, the static friction will increase to match the magnitude of that applied force in the opposite direction until I reach the breaking point. And the breaking point for static friction is the point at which the object is sent into motion. And this breaking point we'll call the force of static maximum. And this will have a similar calculation to the coefficient of, or to the force of kinetic friction, where you'll have mu times mu static, the coefficient of static friction, times the normal force. So that's only when you're at the maximum. You'll have some keywords like the object is just about to start moving, or the object's about to break loose, or what's the hardest that you can push on it such that it will just barely not move. Weird questions like that are trying to indicate to you that you want to consider the maximum static friction force. So let's go ahead and do one of our problems here. This one's going to be in 2 parts. Now the diagram will be the same for both. You've got a block on a flat horizontal surface. There's an applied force to the right, and there is a, I think, what do they call it? A vertical force, P, that's directed upwards. And those have hats on them. There we go. And they tell us the coefficients of friction for the block and the surface. They give us two of them. In my problem, it happens to be that the coefficient of kinetic friction is 0.25, and the coefficient of static friction is 0.4. So if you're given both coefficients of friction, typically it's going to be on you to determine which one you need to use. They won't ever be used in the same calculation. You'll never have a situation where you have both a static and a frictional force. Both a static and a kinetic frictional force. So yeah, so it's going to be incumbent on you. In some problems, they'll just explicitly give you like a coefficient of kinetic friction, and then that there's no static friction given, no static coefficient. And in that case, you can just go ahead and calculate the kinetic friction. All right, so in this problem, they're going to give you the magnitude of the pulling force. The horizontal force is also given, but they're going to give you two different values for the lifting force P. And in each case, you need to determine the magnitude of the frictional force acting on the block. So let's do the first one. I'm going to put up here, by the way, that the magnitude of my force F for me is 5.9. It'll be different for everybody. 5.90 newtons. In part A, for my problem, they say that the pull force has a magnitude of 9.00 newtons. And I'm just asked to find the magnitude of the frictional force. I don't know if it's static or kinetic. I'm going to need to do some physics to determine if it is static or if it is kinetic. So to go back up to our diagram, we can label the direction of our frictional force. We know that it'll be to the left, whatever it happens to be. So we can go ahead and call that F sub F for frictional force. What other forces are acting on this object? Well, in order for the frictional force to work, we need a normal force, we know, and the normal force is always perpendicular to our point of contact. So our normal force will point upward. And we also are always going to have a weight that is directed down toward the center of the Earth. And so if you take a look at this, probably the most forces that we've seen in a single problem so far. Now, there are different methods to solve this. We're inevitably going to use Newton's second law to sum the forces. If it helps, if this was helpful in kinematics and motion, then I would recommend doing a similar thing here, where we will split our problem up into the x and the y. I'm actually going to do this on the next page. So we'll do our x and our y. This is question one. Cool. Thank you, everybody. So if I were to, this is just a way of splitting up this problem. If I were to take this, yes, yeah. If I were to take this problem here and only look at what's going on in the x direction. The x direction, I just have my applied force to the right, and I have the frictional force to the left. So let's just draw like a diagram that just is only concerned with that applied force to the right and the frictional force to the left. And similarly, on the y side, we can just sketch only our y forces, just so we can kind of get an idea of how these two dimensions are splitting up. So we have our normal force and our P force, that lifting force going upwards, and then we have a weight pulling us downward. Now, since we do not know if the object is undergoing static or kinetic friction, we do not know if it's in motion, so we can't say for sure on the left-hand side if the block is going to be accelerating to the right or not. The problem does tell us explicitly the upward pull is insufficient to move the block vertically. So that tells us that for sure there will be no acceleration in the y side. So that's kind of an indication to me that that is probably where I want to start. And I will be summing the forces for the y dimension. And I'm just going to have my normal force up minus the pull force, plus the pull force minus the weight Newton's second law, F equals ma. A is 0, so m times 0 will be 0 on the right-hand side. Okay, in this problem, they gave us the mass of the object of the block. So the mass of the block will allow us to calculate the weight. And they've also given us explicitly the pull force. Now there's going to be two parts, but for both parts now, we can say that the pull force, or rather the normal force, will be equal to, just doing the algebra here, the weight minus the pull force. If you think about this conceptually, generally when you're on a flat surface, your weight and your normal force will be equal. If I apply some lifting force to assist the normal force, I'll subtract that out of the weight, and that will give me what the actual normal force is. Okay, if you don't get that conceptual explanation, it's okay. Hope that might help some people though. All right, so for this problem, we could go ahead and calculate our normal force explicitly. And yeah, since we're just doing part A here, let's just go ahead and calculate that. So our weight is the mass minus 2.5 times acceleration due to gravity, which is 9.8. The pull force for my part 1 is 9. 2.5 times 9.8 is 19.6 plus 4.9. So that's 24.5. 24.5 minus 9 will give me 15.5 newtons. So we have our normal force calculated here. Now, as I mentioned, we do not know if we have static or kinetic. And in order to determine whether we have a static friction or a kinetic friction, we need to figure out if our static friction is broken. That's another way of asking that question. So in order to figure out if the static friction is broken, we want to calculate that force of static maximum, which we know will be mu static times the normal force. My mu static is, was it 0.4? And my normal force is 15.5. I actually need to know what this is. 1 second. Okay. This will give me 6.2. So this is the maximum force of static friction. Keep in mind that in order to break static friction and in order to move over to the kinetic friction regime, I need my applied force, that is in opposition to the force of friction, to exceed this force of static maximum. That's how I break right there. So I simply need to compare this to my applied force. Well, the applied force, as given in my problem, was 5.9 newtons. So if I apply 5.9 newtons and I need 6.2 newtons in order to break through the static friction, is this object going to break through or not? If anyone doesn't see the answer explicitly, I'm applying 5.9 newtons. It's opposed by a maximum of 6.2 newtons. This is my applied, and this is my static friction. If all I have is 5.9 newtons to pull in the block, that's not going to be enough to overcome the maximum static friction. So that's what tells us that we are in the kinetic regime. So we could say for sure we are kinetic. And then we can go ahead and finish off this part of the problem. On the x side, I still haven't done my Newton's second law, so I can sum the forces in the x direction. Now that I know that the object is at rest, oh, I said that this is kinetic. I should have said we did not break the static friction. So this is going to be, yeah, thank you, Nina. We did not break the static friction, so we will be in the static regime. Okay, so I'll go ahead and sum the forces in the x direction. I know that I'll have my applied force, which they've simply called F in this problem. Maybe you'll put an A on it so you don't get confused there. Minus the force of static friction that is opposing it. Actually shouldn't have a vector arrow there because we're just dealing with magnitudes. And again, since we didn't break the static friction, that'll be equal to 0. If I solve here, I get a pretty simple relationship between the magnitudes of these forces. The force of the magnitude of the applied force is equal to the magnitude of the force of friction. Think about that for just a second. This is our maximum static friction, 6.2. But remember our rule back here that the force of static friction is always equal to whatever the applied force is that it's canceling out. So in this case, we have a mathematical result given explicitly that says the same thing. And so that means that our force of static friction will just be equal to the 5.9 newtons of the applied force that is being canceled out by the static friction. So, so this is a bit trickier than any of the force calculations we've done, especially the way that the static friction here varies, and you have to use some physical reasoning to get there regardless to what the actual value is. We're going to do a few more of these. Most of the problems this week are friction based. So we'll go through this process again. One thing that I will say is that for part B, nothing on this page. Oh, actually, sorry, we change the value of P. So for part B, you'll change your P here instead of 9. My P value is 13. So in that case, I'd end up with 11.5 right here. And then when I plug in 11.5 over here, I'll get a smaller force of static maximum, and it'll be small enough that you undergo, that you move into the kinetic regime and you break through the static friction. If you have any questions about that part, feel free to let me know. As I mentioned, we do have quite a few problems today, so I'm going to keep moving through these. Question 2. Now we have a block pushed along a floor. They give us only the coefficient of kinetic friction in problem 2, which is nice of them because that tells us pretty explicitly that we are only dealing with kinetic friction. We don't need to do all that hassle we did in the last problem to determine which type of friction we have. The thing that changes here, here's our block moving along the floor. I usually use lines along the floor to indicate that there's friction, especially when you get to exams where you have some problems with friction, some without. All right, what are our forces on the block? We have an applied force at a downward angle. And yours will be different. Let's just go ahead and say that that's F and that's theta. Other forces here, for free, we always know that there will be some weight, and perpendicular to the surface, there will be a normal force. And if my applied force is pulling the block to the right and it's along level ground, my frictional force will be to the left. And we know explicitly in this problem that that's kinetic friction, so we don't need to worry too much about which type of friction, as I mentioned. And yeah, so we're given our coefficient of friction, we're given the mass of the block, we're given the magnitude of this applied force and its angle. The only thing that we're asked to do is to calculate the frictional force and the acceleration. So both of them will come out of solving this problem, as we did in the last problem. So again, I'd recommend if this helps, I'd recommend splitting the problem up into the x and the y and drawing a diagram for each. What are our x direction forces? We have a component of our applied force. Since our angle theta is given off of the horizontal, we could say that it would be this applied force times the cosine of the angle theta. What is opposing the direction of our motion? We have just the coefficient of kinetic friction in the other direction. The one other thing, of course, we want to be concerned with as we're doing force problems is whether or not we have acceleration in a given dimension. In this case, they're actually asking us to find the acceleration in the x direction. So we are going to have some acceleration. And while we don't necessarily know if it's to the right or left, we can set the right to be a positive acceleration and solve the problem from there. And if we get a negative, that'll tell us it's to the left. On the y side, we are going to have three forces here. So we have our normal force upward and our weight downward. And then we also have a component of the applied force. If the x component was F cosine theta, the y component will be F sine of theta. All right, and then we can do Newton's second law for each of these dimensions. For the x dimension, switch up the colors here. Sum the forces for the x dimension. We have F cosine theta to the right, that's positive, minus Fk, force of kinetic friction. And we're going to set that equal to an ma. We're not setting it equal to 0 this time because we are asked in part B to find an acceleration. So as far as our unknowns here, we have our force of kinetic friction. We do know our applied force and the angle, and we know the mass, but we don't know either the acceleration, which we need to find, or the force of friction, which we also are asked to find. So you could go ahead and substitute in here. You could substitute in your mu n if you'd like for the force of kinetic friction. However, before I do that, I'm going to go to the y side. And the reason is that I explicitly want to find the force of kinetic friction. So I'm not sure quite yet that it's to my advantage to set that in. All right, so just sketch out the net force for the y direction. Upward, we have the normal force, minus downward, we have a weight, minus downward, we have F sine of theta. Our block is accelerating along the ground. It is not accelerating up and down. So here we have force that's equal to 0. Now, since I know the mass and I know my applied force and its angle, I can actually solve this equation for the normal force. Normal force will be equal to the weight plus F sine of theta. And I know everything here. The weight for my problem is 3.1, or sorry, that's the mass. So to make that a weight, you do 3.1 times 9.8. Plus the applied force minus 31. And I have sine of the angle minus 40 degrees. All right. So for me, this will be 50.3 newtons. And this is the magnitude of our normal force. That's very helpful for us because we know that we want to ultimately find the force of kinetic friction. And we know that the relationship between the normal, we know that there is a relationship, right? We know that that relationship is force of kinetic friction is equal to mu sub k times the normal force. So I can find the force of kinetic friction so long as I know my mu sub k. Oh, it's given to me in the problem, 0.24. And my normal force, which I just found was 50.3. Run out of room a little bit there. If I go and solve this, then I'll get a magnitude of about 12 with these numbers. Yours will be different. And that will be part A. For part B, you're asked to find the acceleration. I'll leave that part up to you, but I'll just point out that you now have everything that you need with the first equation, the summing of the forces in the x direction. You have everything you need there to isolate the acceleration, so long as you plug in the givens in this problem. Do you have any questions here? Okay. Next problem brings back a favorite Physics 1 problem type, the block on the incline. But now we're going to do a block on an incline and a penguin on an incline. And the incline has friction as well. So these are kind of the trickiest problems on exams, usually for most people. And it's a pretty safe bet that you'll have a problem like this on your exam. That should have been a theta. I'm not going to draw the penguin. I'm just going to draw it as a block, as I always do. We are given here a coefficient of static and a coefficient of kinetic, which is kind of our worst nightmare. But schematically, I like to sort of indicate that there's friction along that incline. Okay. And in the diagram, they tell you there's applied force up the ramp. I'm going to be careful with which other forces I draw on here. The rest of them, I guess I'll need to add. They give us 3 different scenarios. What is the minimum magnitude of force that prevents the sled from sliding down? What's the minimum magnitude of force that will start it moving up the plane? And what value is required to move it up the plane at a constant velocity? So let's talk through that. Let's just start, by talking through each of those. We're going to have a different diagram for each one. So in part A, I'm going to sort of simplify this diagram just a bit. So in all of these, we're going to have this applied force F. And in part A, we want the minimum magnitude of the force F that will prevent the sled from slipping down the plane. So what is going to be pulling the sled down the plane? Well, that will obviously be the weight. And if the block wants to slide down the plane, if that's the direction of the impending motion, then think about the direction for the force of friction. If the block wants to slide down the plane, then for 1, your force of friction will be opposing that. It'll be up the plane. And a step further, the block wants to slide down the plane, but we want to prevent it from doing so, which means we want to keep it in static. So we have a static frictional force. And then the last thing that we can get from here is that we want the minimum magnitude of the applied force. In other words, if you're going to minimize the applied force and it's in the same direction as the force of static friction, you'd be maximizing the static frictional force. The other forces that I haven't drawn here, I guess the only one that we're missing is the normal force perpendicular to the incline. Okay, let's take a look at part B. Again, we have our applied force up the ramp. In part B, they ask what the minimum magnitude of the force is that will start the sled moving up the plane. So before, in part A, the applied force was simply keeping the sled from sliding down. Now we want to apply such a great applied force that the sled is just about to start moving. That means that the sled now, the direction of the impending motion is up the incline. That means that our force of friction is going to be down the incline. If we want to find a minimum magnitude for F, that's usually like an indication there that we're dealing with that point where the object breaks free. But the minimum magnitude of F that would start the sled moving up the plane, that tells us that we want to just break our static friction. And again, if we're just breaking the static friction, then that would be the force of static maximum. Our other forces here, as before, we have the weight directed downward and the normal force perpendicular to the surface. The last part C. Excuse me. Again, we have our applied force up the incline. Now we want to find the value of that applied force that will move the sled up the plane at a constant velocity. So if we're moving actually up the plane, that means that we have kinetic friction. And since we're moving up the plane, the kinetic friction will counteract that. So we just have our force of kinetic friction. There's nothing to figure out as far as maximum kinetic friction or anything like that. So the problem is pretty straightforward from here. We just have our weight directed downward and our normal force perpendicular. This should be enough to solve the problem. The one thing that I'll point out here is that in parts A and B, we're not moving. And in part C, we are moving at a constant velocity. So for this entire problem, the acceleration will be equal to 0. Yeah, so just to recap this part, in this case, we are applying a force and we're pulling until the block is just about to start moving up the incline. So since the block wants to move up the incline, or we're about to move the block up the incline, that means that your force of friction, your static friction, will be actually keeping the block in rest by being directed down the incline. In other words, it's always going to be in the direction opposite the direction of motion. So in part A, the block wants to slip down, so the friction has to pull it up. In part B, the block wants to slide up, so the friction has to pull it down. In part C, the block is sliding up, so the friction is pulling it downward. Cool. Okay, so as far as the calculation here, it will be very similar for all of them. Obviously, we'll have a different sign convention. I'll go ahead and do one of them. Let's go ahead and let's see. B and C will be similar, so I'll go ahead and do B. I mean, it's not going to matter a whole bunch. But I do want to practice doing the blocks on the incline. So this is just as a reminder, this is part B. So we have our applied force up. We have our force of static max directed downward. We have our weight directed toward the center of the earth, and we have our normal force perpendicular to the incline. Yeah, so Michael, let me work through the problem solving because this is going to look similar for all of them, but there's a pattern here in the way that we do need to actually relate the x and the y. So as we've done before with the block on the incline, set your x direction to be parallel to the incline, your y direction to be perpendicular to the incline. Keep in mind that we have components for the weight. Then we have the x component for the weight will be equal to the magnitude of the weight times the sine of the angle of the incline, and the y component of the weight will be equal to the magnitude of the weight times the cosine of the angle of the incline. It's a little messy there, but we've done that before. Now, as you've done before, it may be helpful to sketch out the two different dimensions, take a look at what's going on in each of them. The x dimension parallel to the incline, in other words, we have our block, we have the applied force up the incline, we have the force of static friction down the incline, and then we also have, as I mentioned, a component of the weight. It'll be W sine of theta. And then for the y dimension, that'll be perpendicular Upward, we have the normal force. And downward, we have just the y component of the weight, which is the weight times the cosine of the angle theta. As I mentioned, for all these problems, the accelerations are equal to 0. We can sum our forces in each dimension. For the y, we have our normal force up. We have our w cosine theta down. You can sum the forces in the y direction, or if we're getting used to this, we could say, those forces must cancel each other out, so their magnitudes must be equal. That's one of our quiz problems this week. Nina, that's just the rule when you have a block on an incline, is that the x component is going to be sine and the y component is going to be cosine. It comes from a little bit of a complicated geometric derivation. So my recommendation is usually just to internalize that that's how the force of gravity will split up on an incline. Okay, for the x, or rather, sorry, what was it here? Yeah, so we have the normal force. Ultimately, what we are solving for in part B is we want the minimum magnitude of that force F that will start the sled moving up the plane. So we can go ahead and sum our forces in the x direction. As I mentioned, you could do the sum of the forces in the x is equal to the F up minus the two forces down, or as we did over on the right-hand side, you could say, okay, so my applied force, since I have no acceleration, my applied force should just be equal to the sum of the magnitude of these two forces here, right? These two are canceling out this one. So that'll be the force of static max plus the weight times the sine of theta. Okay, ultimately I need to solve for this guy right here. So if I can get some numbers in on the right-hand side that I know, then the problem will be done. Force of static maximum is equal to mu static times the normal force plus W sine of theta. And then I know my normal force from the y. I know that the normal force is W cosine theta. So this will be mu sub s times W cosine theta plus W sine of theta. Everything here now is given in the problem. Yeah, I guess I'll go ahead and leave that there. Do you have any questions on especially this slide and doing the forces as we've done here? Okay. Going on to the next one here. We have a child in a toy chest, whatever. It's a rope attached to a block. It's the same thing we've been doing. Rope attached to a block. We have a coefficient of static friction given. And that's going to tell us that we're in the static friction regime. Excuse me. For part C, could we use the, yes, so yeah, just to recap for part C, you do have to use kinetic friction because the block is in motion. Okay, so yeah, so for part A, we're gonna apply a force so big that the chest is on the verge of moving. In other words, for part A, we're gonna have the force of static maximum, and we can go ahead and sketch out our block. We have block, we have an applied force at an angle theta. Those are both given in the problem for part A. And what are our other forces here? Well, we have our normal force up, we have our weight down, and we have our force of friction. As I said, if we're on the verge of moving, that'll be our force of static maximum. Splitting this up into the x and, whoops. Okay, in the x, we just have the component of our applied force. Our applied force is applied at an angle theta, so that would just be F cosine theta because that angle is off of the vertical. I'm sorry, off the horizontal. And to the left, we have the force of static friction, which I mentioned is a maximum. Not going to keep writing that out. If we're in static friction, we automatically know there's no acceleration. We know that these forces are going to cancel each other out. So we know that our force of static friction is going to be equal to the applied force times the cosine of theta. We are asked to find the applied force. We do not know explicitly the force of static friction. If you want to go one further step, since we know it's a maximum, we could say that this is the static coefficient times a normal force is equal to F cosine theta. So of course, we're going to need to find the normal force from the y side. So in the y, we have our normal force applied upward. We have a weight applied downward. And then also upward is a component of our applied force. If we have cosine for the x, this will be F sine theta. Again, no acceleration here. Our normal force plus that component of our applied force have to be equal to the weight in order for all of those forces to cancel out. So in other words, we can write N plus F sine theta is equal to the weight, or you can do the summation of the forces in the y direction and solve that way. What is of interest to us here? Well, we know that ultimately we want to solve for the applied force F, and we now have two equations that relate that applied force to the normal force. Thinking of how to go about this would be less work. Yeah, so it's a system of two equations essentially that we need to solve. My recommendation would be to whenever you'll be faced with this system of two equations quite a bit. My recommendation would be to isolate the normal force in one of the equations, weight minus F sine theta, and then go ahead and plug that in to our other equation. So that will give us, plugging it in for the normal force, mu static times the weight minus F sine of theta is equal to F cosine of theta. Cool. And then from here, we need only to solve for F in terms of everything else. Just to sort of skip ahead to what you'd end up with, you'd have something like this. F is equal to, let's see if I can get this right. Let's see, so we have to factor out, we'd have F cosine theta plus F sine theta mu sub S. And then we have, okay, so mu sub S times the weight over mu sub S sine of theta plus cosine of theta. Okay. Not a beautiful equation here. However, for part A, we have everything that we need to solve. On the right-hand side, we can plug everything in there. And for part B, we want to find a value of theta for which F is a minimum. So yeah, so in order to do that, let me copy this down on the next page. Use of S sine theta, cosine theta. So this is for part B. Yeah. Yeah, so let me just talk through the algebra. We want to isolate F, so we have to distribute our coefficient of static friction inside of our parentheses. And then when you do that, you have this mu sub s times f sine theta, which you'd want to move over to the right-hand side. So then you have f cosine theta and f mu sub s sine theta. That's what ends up becoming your denominator here. What's left over on the left-hand side is mu sub s times the weight, and that's what becomes your numerator, because that's what'll be left over there. I hope that helps, Michael. Okay, what was it? Mu sub s sine theta plus cosine theta. Okay. So our equation that we have is f as a function of theta is mu sub s times w, or the weight, over mu sub s. Okay, I'm gonna actually just start writing mu. We only have one mu in this problem. I don't have to write this a lot. Mu sine of theta plus cosine theta. And in part B, they ask us to find the angle theta such that our force F is a minimum. I have an equation for the force in terms of the angle theta. If I want to minimize that equation, then what I'm going to need to do ultimately is, yeah, Elizabeth, I can go over that at the end if you want to stick around. So if I want to minimize this equation, the equation for the force in terms of theta, then what I need to do, think about where a function is equal to a minimum or maximum. That's when the derivative is equal to 0. So if I want to minimize it with respect to theta, then what I need to find is the derivative of my force equation with respect to theta. Okay, this looks a little scary. I know I said earlier in the class that you'd probably only ever need to do a power rule. Here we're actually going to need to do a little bit more. Low d high minus high d low all over the low. So the bottom times the derivative of the top. The top is actually a constant since we're differentiating with respect to theta. So bottom times derivative of the top is 0, minus top times the derivative of the bottom. That'll be mu w for the top. Derivative of the bottom is mu cos theta minus sine theta. So that was low d high minus, so we did have a minus out in front, minus high d low, all over low squared. Mu sine theta plus cosine theta, quantity squared. Okay. And yes, of course, ultimately we want to set this equal to 0. We're trying to minimize this function. That's going to make our job quite a bit easier. We can freely eliminate our constants out front, and we can multiply both sides by our denominator to get rid of that. And now we have mu cos theta minus sine theta is equal to 0. And then we can isolate here. If I add my sine over to the right-hand side, I'd have mu cos theta is equal to sine theta, or in other words, mu is equal to tangent theta. This is kind of a long-winded way of getting to one of our definitions for mu, which is if you put an object on an incline and increase the angle of the incline at a certain point, the object will break free, and that angle gives you the coefficient of friction according to this relationship. You don't need to know any of that, but if anyone cares and is still listening, that's how you find it. Ultimately, for our problem, all we're concerned with is what that value of theta is. So I just need to take the arctangent of mu, and whatever your mu is will be your answer here. Okay, and then part C, once you found this angle, then you just need to find the actual value of f. So once you've found your angle here, you just go ahead and plug it in with your other knowns there, and that'll be part C. All right, do we have any other questions on this problem? Elizabeth, just to answer your question, just to give you the quick question, if you need a longer one, we can talk about at the end. I think you were asking about problem 3C, but in 3C, the block is moving at a constant velocity. All that tells us is that the acceleration is 0. We're not going to do any constant acceleration or anything like that. All we need to know is that since the acceleration is 0, that means that the net force is equal to 0. That's the most important part. So
the net force is equal to 0. So would that indicate that like the force has to be equivalent to the x direction of the weight force and the kinetic friction?
Yeah, essentially. Mm-hmm. Yeah, so
okay, because I did that and I don't know why, but it's not like, I don't know, maybe I did something weird with the math, but the x direction of the weight force is going to be weight, the magnitude of weight times the sine of theta, right?
Yeah.
Okay.
If you want to stick, if you can't stick around till the end.
Yeah, sorry, I'll stick till the end.
Okay. All right. And if anyone, this goes for anyone, if you ever have a question and you have to like dip out in the middle of this video, like please do not hesitate to send me a message about it. I'll try to get to it before, at least like by the end of Friday. Okay, so problem 5, we're going back to our circular motion, which we touched on just a little bit last week. If you remember last week, we had centripetal acceleration is equal to velocity squared, or speed squared rather, over the radius. Man, that looks horrible, but hopefully you recognize that equation. The acceleration, I can at least make that one look a little bit better. The centripetal acceleration is equal to speed squared over the radius of a circle that the object is moving around. Another equation that we haven't talked about, but that you can probably figure out, is if you have an object that is moving in a circle, and I wanted to calculate the speed as it moves around a circle. In one circle, it's going to move one circumference, which is 2 pi r. That would be your distance. And on the bottom, you'd have to divide your distance by your time to find the average velocity, right? So that time, we use a capital T. It's a special time called the period. If you haven't encountered that yet, you probably encountered that at some point in a math class or something. But these are our two equations. And we're going to need to make use of both of these along with our force equations at various times in the homework. For problem 5, I'm just going to go through this one relatively quickly because I think this is a pretty easy problem. That's for the speed of a point on the rim. The speed is going to come from this equation right here. So they give you the radius and they give you how long it takes to go around one revolution. Those are both given. You literally just plug those into this equation. And for part B, they ask us to find the lowest value of the coefficient of static friction between the basket and merry-go-round that allows the basket to stay on the ride. Okay, this one might take a little bit more thought to get to, but if we were to take kind of a vertical picture here, there's your basket traveling around a circle. And if we had no friction, then this merry-go-round would just spin and spin and spin, and the block would just stay where it is, and nothing would happen, right? So it's actually the friction that keeps the object moving uh, around the circle. And uh, explicitly, that would be your force of friction there. The force of friction, in other words, is the thing that is imparting the centripetal acceleration on the object. Remember, the centripetal acceleration has to be directed toward the center of the circle. It is a turning acceleration. You need a force to provide any acceleration. So here we're just relating our turning force to our turning acceleration. So from F equals ma, you could say that the force of friction is equal to the mass times the centripetal acceleration. And then this, you know already, the centripetal acceleration is v squared over r. And pretty quickly, the problem has broken down into, just a plugin right there. Now, the one note that I will make is that this is a pretty straightforward case where we can just say that our force of friction is our centripetal force. You can probably imagine in a few problems, we're going to have situations where it's not as directly related as that. And we'll have to do the X and the Y forces and do all of that rigmarole. But for now, let's just keep moving through these problems. And I believe the mass is given. Oh, okay, yeah. So there's one more step there, right, Michael? The one other step is that the force of friction is equal to mu times the normal force. Since our basket is just resting on an incline, that normal force will be equal and opposite to the weight. So the force of friction in this problem is just mu mg. And so when you plug that in right here, oops, then you can cancel out your mass from both sides. Okay. And whiteboard crash. Cool. Yes, yeah, they're asking you for the coefficient of static friction. Okay, problem 6. Yeah, so we're going to continue with circular motion. Now we have an object on a string. The object on a string problems are a common application of circular motion. I guess the reason why is because it ties into tension, and they like to include, other forces that you've seen. So if I have an object that I'm swinging in a circle, like if I were to take my charger and let's see if I can do this in a Cool. Okay. So this object is swinging in a circle. First of all, what is the force that is most contributing to this centripetal motion? It's the tension in the string that is keeping the object spinning, obviously. There are other forces involved though, and especially when I'm in the vertical, there are other forces involved. Another question is, where is the object lightest and where is it heaviest? It's heaviest at the bottom of its swing. That's where I kind of have to give it a little bit more oomph to get it through. The reason is that at the bottom of the string, at the bottom of the swing, you have the force of gravity pulling the object in the opposite direction as the tension. So by tension has to cancel the force of gravity and also impart enough centripetal acceleration to keep the thing spinning in a circle. So I will sketch out some diagrams for that situation. The other one that we have to be concerned with is at the top of the circle. At the very top of the circle, the gravity is almost enough to keep the object going. I can't quite get it with just gravity. So at the top of the circle, that's where the tension is least important, and they'll give you some problems where they're like, what if you gave it just the right force, if there was just no tension right at the top? Okay, so yeah, so for problem, oh no, we're gonna do this again? Okay. For problem 6, they give us the maximum tension. Child's going to tie a stone to one end, whirl it in a vertical circle. They give us the mass of the stone. They give us the radius of the circle. And we're going to increase the speed until the string breaks. So first question is, where's the stone on its path when the string breaks? Top of the circle, middle of the circle, or bottom of the circle? All right, at the top of the circle, up here, you need a centripetal acceleration to be constant throughout your motion in order to keep it spinning. At the top of the circle, you have the tension and you have the weight sort of acting in tandem. At the bottom of the circle, you still need to get that magnitude of the centripetal acceleration if you're going to keep this thing going at a constant speed. However, now you have the weight acting in opposition to the tension. So the tension needs to not only cancel out the weight, but it also needs to impart the centripetal acceleration. So that's where your tension is at the maximum. All right, I'm not going to explicitly give you the answer to part A, but there you go. For part B, we want to find the speed of the stone when the string breaks. So the string will break when the tension is at the maximum. I guess I have to give you the answer explicitly. The string will break when the tension is at its maximum value, which is down here at the bottom. And we can do our net force in the y direction. There's no x direction in this problem. And you just have that the tension up minus the weight down has to be equal to the mass times the centripetal acceleration. We do have acceleration here because this object is moving in a circle, and that is the centripetal acceleration that we are familiar with. We're asked to find the speed of the stone. If you don't see all the givens that you have here, we can plug some stuff in. We have tension minus our weight is mg is equal to m times our centripetal acceleration, which is v squared over r. Just to count off here, make sure we have everything. They give us the tension in the problem, they give us the mass in the problem, and they give us the radius in the problem. So you have everything that you need here to isolate the speed. Any questions? Okay. And the next problem, we have a passenger moving along a circular path in uniform circular motion. They give you these two figures. The first one is, the magnitude of the force, the centripetal force, as it compares to the speed of the object. And part A asks us to find the slope of this plot at v equals 8 seconds. So again, we're doing a little bit more calculus in this problem, in this chapter than we have. What type of force do we have here? This is just a very basic, they don't give us any other information. There's not like tension or anything like that. They literally just tell us it's a centripetal force. Well, we know that a centripetal force is equal to a mass times a centripetal acceleration. And we could go a step further and say that the centripetal acceleration is v squared over r. So our centripetal force is mv squared over r. We're asked to calculate the plot, the slope of the plot. The plot is force versus velocity. If I want to find a slope is a derivative. So I would do the derivative of the force with respect to velocity. Differentiating the right-hand side, holding everything else constant, you would have a derivative of 2mv over r. Pretty straightforward. You just need to evaluate it. They've given you a speed explicitly. They've given you the radius and the mass as well. So it's everything that you need for part A. For part B, it's similar here, but they're going to ask you for they give you a second plot, which is force versus period, and ask you to find the slope of that plot. So in order to find, by similar argument, we're going to need to find for part B the derivative of the force with respect to the period, big T. Oops, not a 2. Just going to do a question mark. So in order to find that, we need to substitute out for our speed, v. We need to substitute out something in terms of the period. You recall a few pages ago that I had this relationship that v is equal to 2 pi r on t. In other words, the speed is equal to the distance around a circle divided by the time around a circle. And yeah, we can go ahead and just substitute that into our equation right here. And we have that, or oops, I shouldn't have done that one. I should do this equation here. So new equation will be that the force is equal to m on r times 2 pi r on the period squared. And now this is something that we could differentiate. It's going to be, uglier before it gets better, but it would be something like, let's see, we're differentiating with respect to t. Yeah, I mean, we could do that. We could clean this up a little bit first. So squaring 2 pi gives us 4 pi squared. And then we have an r squared on top and an r on the bottom. So we'll just have 1 r. So it'll be 2 pi squared mr on t squared. Differentiate here to find df dt. 4 pi squared mr is held constant. I need to multiply by the power of the period, which is -2. So we end up with -8 pi squared mr. And then the derivative of t to the -2 is t to the -3. So that'll be over t cubed. And then again, we have an expression, we have some values, we can plug them in. Not sure if we have any other questions here. Yeah, it's a good question. So Olivia asked if, how do we determine the units here? So it'll have the units of whatever the derivative is on the left-hand side. So here we have force over velocity. Force is newtons, and velocity is meters per second. In part B, we have force over period, so that will be newtons per second. In part A, you have to, I think, reciprocate your fraction on the bottom there to get the actual units, but that's a good question. Okay, the next problem I'm just gonna tell you right now is like pretty contrived. These flying circus of physics problems are like, I really hate, they've haunted me for like a decade. I just don't like them. It's not helpful, I don't think, to have problems that are this contrived. But we have an amusement park ride. You got a car moving in a circle. So you got like an arm that like swings in a vertical circle, and there's like a cage or something that people sit in at the end. And so that arm is rigid and stiff. And at points in the motion, it will pull the car like through something, pull it through a swing or something. And at other times it will push it and like keep it up in the air so that you don't want it to go slack, because then the car will go crash in the ground and people are in trouble. That is like the very contrived explanation behind this problem, and how they can ask you to do the following calculation, which is essentially they're not going to tell you if the arm is pushing or pulling. You are responsible for finding it. And they give you the weight, and they give you the radius of the circle. They say at the top of the circle, what is the force on the car from the boom? If the car's speed is as given. And then Yeah, and then they ask you to calculate it twice essentially. So the physics is going to be the same for both. So I could do the setup and then leave it up to you. Hopefully I'll give you something here that's kind of generally applicable. So at the top of our circle, we have an object here flying through a circle. And in order to continue moving through a circle, we know that we need it to undergo some centripetal acceleration. And we know that the weight will be acting downward. We know that another force is this boom force. And quite crucially in this problem, we don't know if that is a force upward, holding the thing up, or if it's a force downward, pulling it back through the motion. What they do tell us is that they want, the minus sign to indicate the downward direction. So what I would do is just kind of generally set this boom force to be upward. And then hopefully, if we're very careful with our signs as we work through this problem, our solution will tell us explicitly if it's upward or downward. Okay. So keeping in mind our usual y conventions that up is positive and down is negative, let's go ahead and sum our forces in the y direction. Acting upward, we have the force of the boom, minus acting downward, we have the weight. We set this equal to the mass times the centripetal acceleration. What is the sign on my centripetal acceleration? If I'm using this convention here, downward is negative, my centripetal acceleration is pointing downward at the top of the circle. So I need to make this a negative centripetal acceleration. In other words, why do we need that negative? Another way of saying why we need that negative is to indicate that the centripetal acceleration is pointing in the same direction as the weight. That's another way of putting that. Okay, so I'm asked to find the boom force. And so far it's looking pretty straightforward that the boom force is equal to weight minus MAC. Of course, I don't have the acceleration explicitly, but what I do know is that the centripetal acceleration is v squared over r. So we could say that our boom force is the weight minus m v squared over r. That r is only in the second term there. There's no r underneath the weight. And yeah, we have everything that we need there. If you plug in the two different speeds given, one of them will give you a positive, and the other one will give you a negative, and you just put those right in to your answer. I did not get rid of the negative sign in front of AC, Michael. The negative sign is right here. This is the negative. It is imperative that you don't get rid of that, because that's what tells you from your original equation. That negative sign tells you that that centripetal acceleration points. Yeah, good. I just wanted to like re-emphasize that, because that is like the one like physics thing that you're doing in this problem, that you want to make sure that you're able to do on other problems as well. Okay. Making good time. It is a beautiful day outside. We're all gonna do our homework. I'm gonna go lay in the sun. All right. Puck on a table problem. This has been a homework problem every semester for decades as well. And has also been a homework, an exam problem many times. Um, yeah, I got my windows open right now, like for the first time in 6 months. It is very nice. Okay, so this problem kind of has it all. One thing is we have a frictionless table, which is cool. But they like this problem because you have two objects. So you have to do the forces on each object, and you also have circular motion. This is why they love this problem so much. So what I would do is I would start by sort of illustrating the physics that are going on in both. Let's say we have a puck and we have the other thing's called a cylinder. Yeah. So let's start with the cylinder. The cylinder's physics are a little more straightforward because it's only in one dimension. You just have your cylinder. This is your mass big M, and that cylinder just has the weight downward, and it has the tension upward. And we know that we want to keep the cylinder at rest, so the acceleration is 0. And as a matter of fact, you could say that that means that your tension and your weight cancel out. So in other words, the tension is equal to the weight, which is equal to big M times G. Okay, and that's basically all you need to do with the cylinder, with the hanging thing. The bulk of the problem is going to come from the puck. So you kind of are tasked here for the first time with viewing this problem in 3 dimensions. What I'm going to do is I'm going to illustrate the puck sort of looking at it from the side of the table. So, and of course it's going to be a rectangle because that's all I can draw. And that's the flat surface of the table. And so this puck is moving around, and we could just say that the centripetal acceleration, without sort of losing any of our generality, is going to be toward the right. So let's say that the puck is sort of where, trying to think of how you see it. Yeah, okay, so here's the puck. The puck is moving this way, and it's about to like turn as it comes out of the page at you. So that also means then that the rope that is applying the tension would be pulling it in that direction, right? So tension in that rope that is causing the puck to move in the circle. Without the rope, it wouldn't be moving in the circle. We also know that what that tension is equal to. And what are our other equations or other forces here? As always, we have a weight downward and we have a normal force upward. We could do our X and we can do our Y if you'd like. For the X side, we have just a tension. That tension is providing the centripetal acceleration, so that tension is equal to MAC. We're asked to find a speed, and they give us a radius. It's a good indication that we're actually going to want to say that the tension is equal to mv squared over r. All right, now you'll see I have 2 equations for the tension here. One of them is in terms of the big mass and the gravity. The other one's in terms of the little mass, the speed, and the radius. And in fact, we can just set these 2 equal to each other. And then I'll have big M times G is equal to little m times v squared over r.
Wouldn't mv be squared since you're multiplying the AC times m here in the tension part?
Say that one more time. So the AC is equal to v squared over r. I just did a substitution.
Oh, okay. I thought AC was always equal to mv squared over r. Okay, thank you.
No, so that's, yeah, so I'm going to clarify that though, because that's a good question, because you'll hear that term. What you're talking about there is the centripetal force. The centripetal force is equal to m times the centripetal acceleration. I think that might be where you're, so
Okay, yeah, no, that makes sense. Thank you.
that's why, yeah, sometimes you'll just, especially in notes and stuff, they're just going to write like the centripetal force is mv squared over r. I prefer to just have to know like AC. Sweet. All right. One more problem. This is a very silly problem. But actually, this is, I think, better than the flying circus ones. So you have a block. A student is going to apply a force to this block, and they're going to push the block along the ceiling. So the surface here, instead of the block being on the ground, the block is pushing up against the ceiling, and you have some pushing force P, okay? And we also have some coefficient of friction. Now, why is the ceiling important? The ceiling is important for one reason. That's because our normal force is always perpendicular to the point of contact, or in other words, our normal force is perpendicular to the surface that we're moving along. So that means that in this case, our normal force, since it needs to be perpendicular, is actually going to be pointing downward. That's what's fun about this problem. Also pointing downward, we have the weight. Since that force is pushing us to the right, we have a kinetic friction force, excuse me, acting in opposition to that to the left. Putting all this together. Yeah, oh, cool. Then the one last thing is that they ask us explicitly for the magnitude of the block's acceleration. So I think every friction problem that we did earlier, the acceleration was 0. Now we finally have a problem where we do not know the acceleration. All right. Last thing I'll put here is that the angle theta there is off of the horizontal. Let's go ahead and do our two different sides. So do the x and the y. For the x, we have the x component of the p force. So that will be p cosine theta. And then we have the coefficient of kinetic friction. I'm sorry, the force of kinetic friction. Also, most importantly, is that this is where our acceleration is. So this might, in case anyone missed that, that's a k right there. F sub k. All right, so if I sum my forces in the x direction, I have my F sub k minus my applied force times cosine of theta. And that's going to be equal to m times the acceleration, where that is the acceleration I'm ultimately looking for. Maybe you'll get a little bit excited here and say, okay, well, I need to find that acceleration. So I do know that my force of kinetic friction is always going to be equal to mu sub k times the normal force minus p cosine theta is equal to ma. I know the magnitude and the angle for my applied force, so I know what the second term right here is. I know this. And I know my coefficient of kinetic friction. The only thing I don't know here is the normal force. And hopefully you're starting to get the hang here that we usually are going to need to go to the y to get our normal force. The force is in our y direction. Upward, we have the other component of the applied force, p sine of theta. Downward, we have our normal force and we have our weight. Sum the forces in the y direction now. We have p sine of theta minus the normal force minus the weight because they're both downward. No acceleration in the y direction. We're accelerating only to the right. So that will be equal to 0. Trusting you to do the algebra here. That's actually just add the normal force to both sides. Normal force is equal to p sine theta minus w, the weight. Now we know everything on the right-hand side because our weight is mg. So we can go ahead and plug in, do a substitution here for the normal force. And when we do that, we'll have mu sub k times p sine theta minus the weight, and then minus the p cosine theta equals mass times acceleration. Keep in mind here that the weight is mg, but I'll leave the rest of the fun up to y'all. And if we have any questions here, let me know. I know that there was one question earlier that I said we talk about. But do we have any more questions on this problem before I stop the recording?
I do have a question real quick. How do we know that, like, why did you make the force of friction positive in this problem, in the x part, when you were summing the x direction?
No, I absolutely should not have done that. I don't know what just happened to my brain. Thank you for thank you for calling that out. Yeah, this should have been plus and minus, well,
Okay, thank you.
which would have been, yeah, what else will that change? Let's see, this will be positive, this will be negative. And then, yeah, be negative there and a positive there. That will change the answer. That'll give you a positive acceleration when you solve. Yeah, Olivia, that's an exam problem that we will do. But not concerned with that for the homework this week.
Thank you so much. Goodbye.
Yeah, all right, see y'all later. Brian, are you still here? Let me stop the
Oh yeah,
recording.
I am.
Okay, let me grab you the link. I'm gonna stop recording if I can find it.